Okay, so our addition polymers are always made from alkenes that are based around our ethene structure. So by that we mean a CC double bond with 4 components. Ethene is obviously with all hydrogens. However, in order to get other polymers, we could have different substituents on any of the 4 or all of the 4 carbons. So we might instead write them as R groups instead of hydrogens, where R could be a hydrogen or it could be a different functional group such as chlorine. Our alkenes, when they're just carbon and hydrogen, have a general formula of CnH2n, and this is because it's unsaturated. So we're familiar with alkanes being CnH2n plus 2, but this is unsaturated because you could still add more hydrogens on to your alkene if you were to break that double bond and add 2 hydrogens onto them. But the unsaturation comes into play because there is a double bond there. And the way that we can test for this is using bromine water, which is an orange solution. However, this will decolorise, i.e. turn colourless, if a double bond is present. And that is because our bromine water adds to our double bond in an electrophilic addition reaction, which we looked at either last week or the week before, in order to add the Br2 onto the double bond, so you then have 2 bromine atoms attached. Alkenes, obviously we are talking about polymers here, so we use them to make polymers. You can also use them as fuels, but they tend to combust incompletely more so, and so you get the smoky flame instead of a clean flame. So not as often used for fuels, mainly used to make polymers, because we can break this double bond to add them into that long polymer chain. So an example of a polymer is polychloroethene, and here we've got our unit repeating in our polymer, and that's due to an alkene being added repeatedly. So here our alkene is chloroethene. As that double bond would break in order to add onto additional ethene molecules to make this polymer. So in the one drawn above, I've got 3 alkenes which double bonds would break in order to join together in order to make that polychloroethene. You can also get what's called copolymers, and this is where you have polymers made up of different alkenes. So where you've got not just the same alkene being added together, but different alkenes being added together. So the example we look at here is our Aqua Acrylonitrile. So again, based around this ethene structure, we've got 2 hydrogens and 1 carbon, hydrogen on the second, and our nitrile group, and we're adding that with our chloroethene, and so breaking our double bonds to add these molecules together. And of course they carry on. This is just one way in which it could form, But if you were to rotate them in various manners, then you're going to come up with different ways in which they can alternate. As it's a 50-50 ratio though, you'd expect it to be 1, then 1, then 1, then 1. However, addition polymers, and we'll look at condensation polymers next year, these are non-biodegradable, as they're not easily broken down. And the reason for that is because if you look at the bonds in which you're going to have to be breaking, it's your CC bonds or your CH bonds, or again CC bonds, which are very strong. So you have to break strong CC covalent bonds, and this requires a lot of energy, which of course is not going to naturally happen at our standard temperatures. We did also look earlier this year at the difference between low density polymers and high density polymers. So high density polymers had no branching, whereas low density polymers, you have branches coming off your polymers. And what this means is that they can't pack as closely together, and so you're going to have weaker intermolecular forces. So there's not much holding those molecules together, and so this means that it's quite a soft and flexible material. And so, for example, our low density polyethylene we use for our plastic carrier bags, whereas high density you've got close packing, as there's no branching, and so you have stronger intermolecular forces, and so this is quite a hard and rigid polymer, and so instead this can be used for plastic boxes, much more sturdier structure than those plastic bags, all because of there being no branching compared to the branching.